Hello, welcome back to Educator.com and welcome back to Physical Chemistry. So today we're going to talk about term symbols and atomic spectra. Let's jump right on in. I'm sorry if my voice is a little scratchy today. I hope that I'm still well understood. Okay, so we've talked about term symbols, and now let's see what the association is with term symbols, what the association is with atomic spectra. So let's actually go to blue, I think. So term symbols, they're also called spectroscopic term symbols. Also called spectroscopic. Spectroscopic term symbols or spectroscopic symbols. Because the lines we see on atomic spectra, like the one that you see below, which we'll talk about in just a minute, they represent transitions between electronic states. Between electronic states. And electronic states, as we saw in the previous lessons, they're represented by term symbols. And electronic states are represented by term symbols. Okay, so we've seen spectra like this before. I mean, we saw it early on in the course when we were talking about the evidence, some of the early evidence for, for the quantum theory. So we go ahead and we take an atom, we excite it, we excite the energy to a higher level, and then we allow, and then it falls back down to, the excited electrons fall back down to a ground state. When they fall back down, they emit that particular excess energy as photons of light, but they emit certain frequencies. That's what we see here. The higher they go, they fall down, the higher the energy. And of course, at some point, it hits some upper limit. So that's all these are. It's just, it absorbs light, it absorbs energy of a certain frequency, and then it spits it back out when the electron falls back down to the ground state. Okay, so this particular one is the Lyman series for atomic hydrogen. Okay, so this, let me do red now. Yes. This right here is the Lyman series for atomic hydrogen. Atomic hydrogen. Okay, this series the Lyman series represents transitions from higher n values, the first quantum number, n equals 1, 2, 3, 4, 5. So higher n values, and let me put in here in parentheses. Actually, let me just continue it down here. These higher n values, you remember n is the primary quantum number, down to the ground state. Which is n equals 1. So this represents transitions from level 2 to level 1, level 3 to level 1, level 4 to level 1, and so on. So level 2 to level 1, that's that line. Level 3 to level 1, that's that line. Level 4 to level 1, that's that line. So we knock the electron in the 1s, right? The electron configuration is 1s1. We knock it up to our 2p, and then it drops back down. We knock it up to 3p, drops back down. We knock it up to 4p, drops back down. It's getting higher and higher energy. When it drops back down, it emits a photon of light. higher and higher, higher energy. That's all that's going on here. That's what spectra represents. These names, don't worry about it. Lyman alpha, Lyman beta, Lyman gamma, that's just first level, second level, third level, or in this case, actually n equals 2, n equals 3, n equals 4. That's unimportant. Here we have the wavelength given in angstroms. Oftentimes we'll see spectra given in inverse centimeters. For our purposes, we're going to be working mostly in inverse centimeters, which is the wave number. And there are ways of converting between the two. That's not important. What's important is the numerical value and the qualitative information that we get so far. Okay. Now, when we look at the first line, so let's go ahead and take a look at this line. When we actually look at that line under a higher resolution, in other words, when we magnify it, when we look at the first line, and the second and the third, actually, not just the first, when we look at these lines for the Lyman series, when we look at the first line, under higher resolution, let's actually spell things properly here, getting a little ahead of myself. Under higher resolution, we end up actually seeing two separate lines. So this single line that appears in this spectra is actually made up of two individual lines that are really, really close together. Okay, we end up seeing two separate lines. Two separate lines. The question is, what's going on? It jumps up from, so we excite it from level 1 to level 2, and then it drops back down to the ground state, emits that energy. That's what we see here. It emits a photon of a certain frequency, and that frequency, in particular, this particular wavelength, happens to be that. Well, okay, so it jumped up from one state, ground state, to a higher state, and it dropped back down. We should only see one line. Why are we seeing two lines? When we see two lines, each line represents an energy level. So basically what's happening is it's jumping up, and then it's dropping back down, but it seems like there are two different levels. Either it's jumping up to two different levels, and each of those levels is dropping back down. So if this is the ground state, it's either jumping up to here and jumping up to there, so that when these fall back down to the ground state, you're getting two lines, because there are two different energy levels, very, very closely spaced, that ends up looking like one line under a lower resolution. Or we have a double level jumping up to a single like that, so it's dropping, but these are going to end up being the same energy. So more than likely what's happening is that you have the ground state, and then you have two higher energies, but what is it that's actually going on? So let's take a look. So we ask ourselves, what's going on? Okay,